The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
I hope you're all recovered from the quiz. Our apologies for hard questions, but it's just the first quiz. We have a lot more fun things to do in 006. So today's lecture is a light lecture. I would even call it a recreational mathematics lecture. And so thanks for coming. I'll make it worth your while. All right? So we're going to talk about irrationals. The motivation behind this is really that every once in a while we're going to have a situation where we want to compute with numbers that are much longer than 64 bits, which is really the word length in a standard computer these days. It used to be 8 bits back in the day. For most of my adult life, it was 32 bits. And recently, Intel and AMD have gone to 64-bit processors. But 64 bits ain't near enough. If you want to do what's called high-precision computation, you want to find precisely the weight of a neutrino, if you're a physicist, for example. And that you're talking about literally 100 decimal digits, which is obviously much more than 64 bits. And that's just one example. So what happens if you want to compute the square root of 2 to 1 million digits, or pi to 10 million digits? How do you do that on a computer? So that's what we're going to do for this module, which is a short module on numerics. We'll have a lecture today and another one on Tuesday, telling you about techniques that use, among other things, Newton's method to compute irrational numbers, as one example, to arbitrary precision. And for your problem set, you're going to look at a different application that corresponds to encryption, RSA encryption, where you have to work with primes. These are now integers, but you work with primes that are thousands of bits long. Right? So again, much more than 64 bits. And so you have to think about how you're going to multiply numbers that are thousands of bits long, how you're going to divide numbers that are thousands of bits long. And that's really the purpose of this module. All right? So let's start off by talking about irrationals. And Pythagoras, whom I'm sure you've all heard of, is credited with the discovery that a square's diagonal and its side are incommensurable. So you can't really express the ratio as a rational number, as a ratio of integers. Right? Now, it turns out that the Babylonians and the Indians knew this way before Pythagoras, but he gets credit for the Pythagoras theorem. And he was also a Greek philosopher. In fact, maybe he was first a philosopher and then a mathematician. And he espoused a philosophy that I guess is called Pythagorean mysticism, that said that all is number. Okay, so the world is about numbers, and he worshipped numbers. His followers worshipped numbers. And the problem here was that he didn't really like the square root of 2 because he couldn't express it as a number, or what he thought of as a number, which was 1, 2, 3, etc., the integers, whole numbers. So he called this ratio speechless. Something that he really couldn't explain. Okay? And irrationals were actually considered a threat to the mystics because they couldn't really explain what square root of 2 was. They'd try and measure it, and they wouldn't come up with the right answer, because the next time around it would be a little bit different if they did things a little more precisely or not so precisely, and it bothered them no end. And so they tried to find patterns in irrationals because they considered them a threat, and they obviously didn't find patterns. But imagine if we could actually find patterns, right? I mean, that would be a really big deal, right? I mean, it'd be better than P equals NP, if you know what I mean. If you don't, it doesn't matter. So that's another motivation for high-precision arithmetic. Let's try and find patterns in irrationals. If you go to millions and trillions of digits, maybe it's just a matter of time before we discover that there's no such thing as irrational numbers. Okay, who knows, right? So let's do that for the rest of this lecture. Let's try and figure out how we're going to compute irrational numbers, or things like square root of 2, to arbitrary precision, so we can go play around, and we'll give you some code and you can play with it. So if you look at square root of 2, I'll just put this up here. So it's 1.414, and you probably all knew that. Then it's 213, 562, 373, 095, 048, etc. And I mean, I don't see a pattern there. I mean, I see a zero, a couple of zeros here. It's kind of hard to imagine. You'd probably want to think of a computer program that generates square root of 2, and then maybe a different computer program that's looking for patterns, right? So let's not worry about the square root of 2. I want to digress a little bit. I did say this was a bit of a recreational mathematics lecture. And let's talk about something completely different, which are Catalan numbers. So these are really my favorite numbers in the world. And people like primes. Some people like irrationals. I like Catalan numbers. Okay, Catalan numbers they show up all over the place. And how many of you know what Catalan numbers are? Oh, good. Excellent. So Catalan numbers have a recursive definition. You can think of them as representing the cardinality of the set P of balanced parentheses strings. And we're going to recursively define these strings as follows. We're going to have lambda belonging to P, where lambda is the empty string. And that's rule 1. Rule 2 is if alpha and beta belong to P, then I'm going to put a paren, open paren on alpha, close paren, and then beta, and that belongs to P. Okay? So you iteratively or recursively apply this rule over and over, and you start getting strings that are balanced, right? So this is balanced. Now that's not balanced. This is not balanced. And so on and so forth. Obviously, things get more complicated in terms of the parentheses when you have more brackets or parentheses. And so the nice thing about this definition is that you can get every non-empty balanced parent string via rule 2 from a unique alpha beta pair. So as an example, suppose you want to generate the string that looks like this. So that's a little more complicated than the strings we've looked at so far. Then you obtain that by having alpha be this simple string, and then you put the brackets around that, and then your beta corresponds to this. right? So now alpha and beta were previously generated. So if you apply rule 2 to the empty string, with alpha being the empty string and beta being the empty string, then you get this thing here. And obviously you could get beta by setting alpha to be the empty string and beta to be this string that you just generated, and so on and so forth. Okay? So you just keep going, and the strings get longer and longer. The cardinality of the set gets bigger and bigger, and those are the Catalan numbers. Okay? And so this is a non-trivial question, which is I'd like to enumerate the Catalan numbers and compute and get an analytical form for the cardinality of the set. And that's really what the Catalan number is. It's the cardinality of the set. And so Cn is the number of balanced parentheses strings with exactly n pairs of parentheses and I have C0 equals 1, which is my base case, right? And that's just setting, it's an empty string. So I'm going to say that the empty string is a string, and that's just setting up the base case. And now I want an equation for Cn plus 1. And I need to use the fact that I can get Cn plus 1, a particular string that belongs to this set where I have n plus 1 parentheses in a unique way from a string I've previously generated that was part of either the set that had n parentheses, or it was combined using strings where alpha was in some set that was maybe generated a while back with a small n or something that's significantly smaller than n, and another thing that was generated, a beta that was generated later or maybe at the same time, etc. So can someone tell me what an equation would be for Cn plus 1 based on the Ci's that are less than n? So what about C1? Maybe I'll ask, what about C1? What's C1? 1. Right? C1 is 1 because all I have is this string. That's the only balanced string. Right? Now I have C0 and C1. What's an equation for C2 in terms of numbers? I want a number for C2 based on C0 and C1. Someone? Yeah? C0 plus C1? No, not quite right. How many strings do I have? C0 plus C1. Yeah, actually, you're right. Well, the number is right, but the equation is wrong. Okay? It's not quite that, right? You get a, yep.
So it's something like
C1 times C1 plus C1?
yeah.
I think you want to use the C0.
Okay,
C0. But that's not quite right either. Someone else. Yeah, okay, you. C0 times C1. C2 would be C0 times C1 plus C1 times C0. Okay? And you're setting the alpha. So here's the thing. You set the alpha and you choose the alpha, and then you choose the beta. Okay? And there's a couple of different ways that you could choose the alpha. Right? You could choose the alpha from, you could make it a string that's empty, or you can make it the one string that you've generated so far, which is, the standard simple string, the non-empty, the non-trivial balanced string. And you could do that a couple of different ways with the alpha, and that's why you have two terms over there. All right. So the number in terms of all the equations I got, they all came out to be the same. It's 2, and that's correct. Okay. But this is the equation for it. And so now tell me what a general equation is for Cn plus 1 based on what we've learned so far for the C2 equation. Yeah, back to you.
So C0 times Cn plus C1 times Cn minus 1 all the way to Cn times C2.
Perfect. Okay, good. That deserves a cushion. All right, good. No, that wasn't me. That was you. And put it right there, right? Bread basket, right? So Cn plus 1 equals sigma. So you gave me a summation, k equals 0 through n, ck Cn minus k, where n is greater than or equal to 0. Okay? And you can figure this out. It's not particularly important as to exactly why this is true. You can think about it offline. But the interesting thing is that this is a generator, obviously, and it's going to give you a nice-looking set of numbers. And I came in early and and wrote the Catalan numbers up on the board, going from C0, C1, C2, etc., just in case you ever see these numbers in real life, right? Or when you're writing computer programs, or you're driving on the road, the next time you see a license plate 4862, turn around and tell your mom or dad, hey, that's the Catalan number, right? And maybe she'll be impressed, right? This, of course, you're not going to see on a license plate, but you could always make up a bumper sticker or something, and you could have, the C17 as being a bumper sticker on your car, right? I mean, that's the kind of thing I'd do. But anyway, so just in case you see these numbers, we might come back to this a little bit later in the class. But yeah, 42 is on that list. Yeah, it has to be. 42 is on every list, right? 42 is the answer to every question. Right? I'm glad you guys didn't put 42 down in the answer to every quiz question. It doesn't quite work, all of the time. All right? But most of the time, 42 is a good answer. Okay? Most of the time. Right? Okay, good. All right. So let's get down to business, right? So we talked about Catalan numbers. It's a digression. If you see them, you'll recognize them, I think. Let's talk about how we could compute. Let's go back to irrationals and talk about how we could compute square root of 2 and other things to arbitrary precision. So what I want to do is to talk about Newton's method. And Newton's method is something you probably learned about in middle school, high school. And let's say you have a function y equals f of x, where this is x and that's y, the coordinate axes. And we're going to try and find the root of fx equals 0 through successive approximation. And for example, we might have f of x equals x squared minus a, right? And if a is 2, then you're trying to use Newton's method to find the root, and you're going to end up with trying to compute square root of 2, or plus minus square root of 2 in this case. But you can go for a particular root, and you'll try and converge to that. So the way Newton's method works is it tries, geometrically speaking, it tries to find tangents, and a different colored chalk would be useful here, but you don't seem to see one. So what would happen is, let's say you're sitting out here, and it's a successive approximation method. So this would give you x of I, and now you want to compute x of I plus 1, and what you're going to do is draw a tangent like so, and find the intercept onto the x-axis, the x-intercept, and that is going to be your xi plus 1. Okay? And you have to write an equation for that tangent, and this is, I guess, trying to figure out how much of middle school math or high school math that you remember. What is the equation for that tangent? Anybody? The equation for that tangent. What do you do in order to compute that tangent? Give me a name. Derivative, thank you. So what's the equation for that tangent? Y equals someone? It's a good thing your middle school, high school teachers aren't here, huh? Not you. You already got a cushion. Someone else? Someone else? All right, I'll start giving you some hints here. F of xi plus f prime xi. Thank you, thank you. All right, you get a cushion. I'm getting whatever it takes, you know. Here you go. Yeah, that was left-handed, by the way. I'm actually right-handed, as you know. Right. So, so what do we have here? So we have f prime xi. Now, come on, let's finish it. Finish it. Times x minus xi. Thank you. Okay, so now I get it. You thought this was too simple a question. You guys were insulted by the question, so that's why you didn't tell me what it was. At least that's what I'm going to pretend to make myself feel better. So y equals f of xi plus f prime xi, which is the derivative of f evaluated at xi times x minus xi. That's the equation for the line. Okay, and that's essentially what we have to do to compute things like square root of 2, which is iteratively apply Newton's method. The only problem is, this is all good in theory, that we can do, take that equation and turn it into xi plus 1 equals xi minus f of xi divided by f prime of xi. Okay, and if you end up doing f of x equals x squared minus a, then you have xi plus 1 equals xi minus xi squared minus a divided by 2xi, which is the derivative of x squared minus a, evaluated at xi. And finally, you get this equation, xi plus a divided by xi divided by 2. Okay? So it's fairly straightforward. Xi plus 1 equals xi plus a divided by xi divided by 2. And if you look at this, remember that a is typically a small number. I mean, it's 2 in this case. If you're computing square root of 2, it may even be an integer, maybe a fraction. But you have to do a division here. Okay? And remember that since we want to compute things to millions of digits, potentially, these numbers, the xi numbers, are going to have millions of digits, right? And so if you end up running this Newton method on a equals 2, then if I simulate what happens without worrying about the implementation, then this is what you'll get. You have x0, you start with x0 equals 1 with a bunch of zeros. X1 equals 1.5 with a bunch of zeros, etc. And then x2 equals 1.41, 6, 6, 6, etc. That goes on. And we're not talking about fractions here. We're talking about floating point numbers, though are integers with a certain amount of precision. So you've decided that you want to compute this to d digits of precision, where d may be 1,000,000. And so you really here you would have a representation that's 1,000,000 digits long, that where basically everything is 0, and here everything but 1 is 0, or maybe a couple if you count the 1 here. And here you have all these 6s here, and so on and so forth. And you keep going, and you get x2 equals 1.4142, 15686. And I want to write one more because I want to point out something that's important. 1.4142, 13562. And what's nice about this, if you go compare it with what you have up there, is that you have quadratic convergence using the Newton's method. Okay, and what do I mean by that? Well, quadratic convergence is a nice property. It's much better than linear convergence. Linear convergence would mean that you get an extra digit of precision for every iteration. Okay, so in this case, actually, a quadratic is better. Okay, usually we think of quadratic algorithms and we kind of throw up. But linear algorithms is what we like, right? But in this case, it's actually a good thing. You have this quadratic rate of convergence where the number of digits that are correct doubles with every iteration, as you can see. So here you have you start with roughly, if you rounded this up, you would get 5. So you're saying that that's kind of 1 digit of precision in terms of the decimal. And then now you're talking about 41, 4142, 4142, 13, and 56. So that's 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 digits of precision here, 4 here, and so on and so forth. Okay, so that's nice. That's why the Newton's method is actually used in practice, because the number of digits doubles. Digits of precision. So now you don't get too scared about calculating things that are 1,000,000, because you kind of go and say, whoa, I mean, that's not so bad. That's only a logarithmic number of iterations, right? It's not like you have to run for 1,000,000 iterations. You go 2, 4, 8, 16, and now that exponential helps you. The geometric series helps you. Okay? So that's the nice thing about the Newton's method. You haven't quite told you how we're going to compute the most important thing here with respect to a divided by xi. Right? So this is just additions. You can imagine that if you have long numbers, you'd end up doing addition fairly straightforwardly, because you only have to worry about one carry, right? And so you go off and I'm sure you've added up numbers that are tens, if not hundreds of digits long. But I'm guessing you haven't manually multiplied numbers that are hundreds of digits long. And if you have, I'd be impressed, though I won't believe your result. But that's something that is kind of a painful thing to do, and so that's why we need computers. And that's multiplication. And has anybody divided a 100-digit number by another 50-digit number? No, right? So you need computers. Okay, so we got to be able to do that division there, a divided by xi, using computers. And so that's really the purpose of this in the next lecture. We're only going to do a high precision multiplication here, and try and see what an algorithm would be for high precision multiplication, because what we're going to do is essentially take the reciprocal of 1 over xi and then multiply that by a, and we need division is going to require multiplication. You don't really see a multiplication there other than a times 1 over xi, and you can say, well, do we really need multiplication? Well, the answer is the division algorithm that is used in practice, and most division algorithms have multiplication as a subroutine. Okay, so we're going to have to figure out high precision multiplication first. It's a little bit easier than division, and use it as a subroutine for high precision division, which we'll do next time. Okay, so now we're sort of back in 006 land, if you will. We have a problem that's high precision multiplication, and we want to find an algorithm for it. And there's the vanilla algorithm that is going to take certain amounts of time, asymptotically speaking, and then there's better and better algorithms. As you can imagine, multiplication is just such a fundamental operation that people have looked at trying to reduce the complexity of high precision multiplication. So if you have n bits, so what's the standard algorithm for multiplication take if you have n bits of precision? N squared, right? But you can do better, okay? And people are, work on it. You can do fast Fourier transforms. We won't quite do that here. If you take 6046, you'll probably learn about that. But we'll do a couple of algorithms that are better than the order n square method, okay? And we'll do one of those today. So the way we're going to work with integers, one little point that I need to make before we move ahead here is generally we're going to say, for the purposes of 006, that we know the digits of precision up front. Okay, so if you want d digits of precision, maybe it's 42, maybe it's 125. In the case of your problem set in RSA, we're going to have it, 1024-bit numbers, maybe 2048. So we know d beforehand, right? And so what we want is an integer which is 10 raised to d times square root of 2 of floor, and which is essentially the same as that, 2 times 10 raised to 2d. Okay? So we're going to treat these as integers, so we don't want to worry about decimal points and things like that. All of these things are going to be integers. And there's no problem here. We can still use Newton's method. It just works on integers. And let's take a look at how we would apply Newton's method in standard form. And we won't really get to the part where we're going to go from division to multiplication today, as I said. We're just going to look at how you can multiply two numbers. So I didn't mean to say that we're going to look at Newton's method. We're going to look at high precision multiplication, and then eventually we're going to use that to build Newton's method, which requires the division. So I have two n-digit numbers. And the radix could be, the base could be 2, 10, normally, doesn't really matter. 0 less than x, less than y, strictly less than r raised to n. That's standard for the ranges. And what I have here is, the way I'm going to do this is use our favorite strategy, which is divide and conquer, because I have n, which is large, need to break things down, break it into n by 2 digit multiplications, and when finally I break things down and I get down to 64 bits, I just run one instruction on my computer to multiply the 64-bit numbers. And standard machines, you could get 128 bits of result back when you multiply 64-bit numbers, right? So in some sense, you only go down. You don't go down to 1 bit. You go down to 64, and your machine does the rest. So what we have here is you set x to be x1, where x1 is the high half, r raised to n over 2 plus x0. So x1 is the more significant half, and x0 is the low half. And the same thing for y. y1, r raised to n over 2 plus y0. And you have now the ranges change. X0 and x1 are smaller. So that's what you have for x0 and x1. Same thing for y0 and y1. So that's a fairly straightforward decomposition of this multiplication operation. And again, if you do things in a straightforward way, you will create a recursive multiply, as I'll write here. And what you do is you say let z0 equal x0 times y0, z2 equals x2 times y2, and I missed z1, but z1 equals x0 y1 plus x1 y0. And I have overall z equals xy equals x1 y1 times r raised to n plus x0 y1 plus x1 y0 times r raised to n over 2 plus x0 y0. And this part here was z0. This part here was z1. And this part here was z2. And if you look at it, you need 4 multiplies, right? 1, 2, 3, 4. And you need 4 multiplies of n by 2 digit numbers. And by now, after you've prepared for quiz 2, I will just say that it will take theta n square time, okay? Because your recursive equation is tn equals 4t of n over 2, okay, plus the linear time that you take for addition. So this is tn equals 4t of n over 2 plus theta n, okay? And you're assuming that the additions here take linear time. All right? So that's how you get your theta n square algorithm. And we're not happy with that. We'd like to do better, okay? And so how do you do better? Well, there's many ways of doing better. The simplest way of fairly substantially lowering that complexity is due to a gentleman by the name of Karatsuba. This is one of those things where if you were born early enough, you get your name on an algorithm. And what happens here is, using the z's that I have out there, you essentially say, look, I know z0 equals x0 and y0. I'm going to go ahead and multiply. z2 equals x2 and y2. Go ahead and do that. And now I'm going to write z1 as x0 plus x1 times y0 plus y1 minus z0 minus z2. So you're actually computing z0 and z2 first, and then using them to compute z1. Okay? So someone tell me why this is interesting, and just take it all the way to the complexity of an algorithm. What is, explain to me why this is interesting and why Karatsuba's algorithm has, I'll give it away, a lower complexity than theta n square, but tell me what it is. Right? Someone other than you? Someone way at the back. Yep, out there. n raised to Log base 2 of 3. That's exactly right. And why did you get that? Explain to me how you got there.
You're using 3 products.
That's right. So first insight is that we're only doing 3 multiplications here. Additions are easy. And we're doing 3 multiplications as opposed to 4. Okay? So tell me how that equation changed of Tn. Tn equals 3 times T of n over 2 plus theta n. Okay? Because you're doing 3 multiplications rather than 4. Multiplications are the complicated operation. Divisions are even more complicated. But additions are easy, and you can do those in linear time, okay, for n digit numbers. And so if you do that, and then you go off and you say, well, that tells us that Tn equals theta of n raised to log 2 of 3, which is, by the way, theta of n raised to 1.58, roughly speaking. And I do not want to compute that to arbitrary precision, though I could. Okay, but that goes on and on. Once you grab this after you're done, right? But that just goes on and on. 1.58 is a rough approximation. Okay, that's an irrational number too. Assuming you think that irrational numbers exist, that's an irrational number. Okay, so good. That's really all I had. By the way, it's 1.58490.625. I really should have written that down. 1.58 in the context of this lecture. I think it's important that we get at least a few digits of precision. Okay. Now you can imagine that you could do better than this, and it turns out that we'll talk a little bit about this next time. But you can imagine breaking this up into not n over 2 chunks, but n over 3 chunks, right? Why don't I just break up x into the top third, the middle third, and then the bottom third, and then try and see if I can get away with fewer than 8 multiplications, right? Because the original thing would have taken 8, and if I can do less than 8, maybe I can reduce that 1.58 number. Okay, so that's a little bit of a preview for what we'll do next time. But what I'd like to do is do a demo, and I want you to run that. It's out there, so blank that out for a second, right? What I'd like to do is really look at a different problem than square root of 2, and show you a demo of code that Victor wrote that computes this particular quantity that you would argue is irrational to arbitrary digits, though we'll probably only go up to about 1,000 or so today. And we'll just look at root 2 is kind of boring, right? It's been around for a while. Let's go back and remember high school geometry. Okay, so I think your high school teachers would like this lecture. Nice little review. So what is that? Well, that's supposed to be a circle. Okay, in case you had forgotten, right? That's supposed to be a circle. Okay, and the circle here is a really big circle. Okay, it's 1 trillion units long. All right. I'm into big numbers today. Okay, big numbers. All right, and the center of the circle is C. Okay, C for center. That is what's called a radius, in case you'd forgotten. Okay, and that's B, and this is also a radius. Okay, and that's A. All right, and what I'm going to do is I'm going to drop a little, I guess, the perpendicular down, which is 1 unit high. So the way that this is structured is that this is 1 unit high. This obviously is, someone tell me what that is. CB. 500 billion, right? That's 500 billion. And obviously CA is 500 billion, right? And if I call this D, somebody who remembers high school or middle school geometry, give me an equation for AD, and that's definitely worth the cushion. Okay? So what's an equation for AD, guys? Yeah, go ahead.
The radius 500 billion minus the
Square root of, yeah.
minus the square root of 500 billion squared minus
Perfect, perfect. Okay, good. So AD equals AC minus CD, and that is going to be $500 billion. Okay, that's 500 billion. You know, that's a little bit less than bailout money, but you know, it's close. 500,000 minus square root of 500. This, when you start squaring this, of course, now you're in real big money. But 500,000 square minus 1. Okay, so forget the square root of 2. You can put the screen down. So is it on, the projector?
It's on, it's just muted.
Okay, you can turn that on. So what we're going to do is, I'm just going to show you the digits of this crazy quantity being computed to tens of thousands of digits. And you'd argue that this is something clearly that isn't a perfect square, right? I mean, you took a perfect square, subtracted 1 from it, and so you have an irrational quantity that's going to go on. And let's see what numbers, what it looks like, right? Okay? So. Get out of the way. I hope you can see from the back.
Oh man, really?
Looking pretty good so far. Looking pretty good. Okay. Somebody see the numbers somewhere else? Have you seen these numbers before? No. Like 20 minutes ago? Like right in front of you? Okay? All right. So I think that's a good place to stop. All right? If you want an explanation for this, I think you can go to section tomorrow. I'm getting you some attendance tomorrow. All right? Happy to answer questions about the rest of the lecture. And thanks for coming.